Hello. So I'm going to be talking about one of the models that Bill referred to in his talk about the Dream 2 deep study, and where we focused all of our various models on application to Phobos. So I'm going to talk about impact gardening. That's the process by which you have impacts coming in, and they create craters, and then they also are responsible for breaking up the bedrock and overturning regolith and mixing the exogenous material and the endogenous material. I have a model that simulates this. And it's a Monte Carlo model, and in a single run of the model with seed for the Monte Carlo model, what I do is I take the crater production function here, showing the number of craters that you get at a certain size as a function of time. And as of right now, I have only run my model up to 1 billion years. So we're just handling 1 billion years worth of cratering. But anyway, and I'm using this lower line here, which is assuming that Phobos has been a satellite of Mars for a very long time, as opposed to being a captured asteroid. So that tells me the number of impact craters that I need. And then I use the size frequency distribution function of the craters on Phobos to distribute those with size. I simulate from, here we go, from the largest down to about, I can't remember if I did 50 centimeters or a meter, but that's a lot of craters when you get down to those smaller sizes. And then what I do is for each of those craters, I implement them in the model. I'm tracking the topography of the surface. And what I do is I calculate the position of the impactor on the surface, and I will create a bowl with dimensions with d over d of 0.2, so the depth to diameter ratio, the height of the rim of 0.036 compared to the diameter, and then the diameter of the ejecta blanket annulus compared to the diameter of the crater of 2.35. These parameters make a volume ratio of 1, and that's something that I do alter on some of the other runs to explore how that affects the resulting topography. So what I do is I take whatever area is within the bowl and reset the altitude to match the bowl shape. And then I calculate the thickness of the ejecta in the annulus outside, and I implement that on top of the existing topography. And I calculate or track the evolution of the altitude of the surface within a 20 meter by 20 meter box on the surface. And I track only 2 numbers in this simulation. I track the current altitude of the surface, which this is showing a transect here. So the red line here is the current altitude of the surface in those places where you see those craters. And I also track the minimum altitude of the surface. So the black line is the lowest point or depth that was ever there. So you can see here we've had a crater that's been filled in with some ejecta as time has gone on. And so then what I can do is with those 2 values, I can derive an effective regolith thickness, or really it's the thickness of the processed material. So if you've never had anything that's disturbed below this line, then that material has not been processed by impacts. And then by knowing the difference of that gives you the thickness of processed material and also the depth to get to unprocessed material. So in a single run, I have run these out to about 1 billion years. But then what I do is I do a set of 100 different runs with different seeds and then compute statistical averages of how parameters evolve with time. So here's just one example run where I have the topography and the regolith thickness evolving over time. Here's after 10 million years. You can see you have a lot of really small craters. And then after 100 million years, you can see that the effects of the larger craters, which are less frequent, are starting to dominate the surface expression there. And then after 1 billion years, you can see you've got a couple of big events that are really dominating what is visible. So I did sets of runs for different values of this volume ratio. So the volume of the excavated or the ejecta material to the volume of the excavated material. And so when you're breaking up bedrock, you can increase your VR because you're taking less dense material and you're making it, or more dense material and making it less dense. But on Phobos, escape is what's really happening a lot. You have a lot of this ejected material that's escaping, and so that's going to decrease your volume ratio. Also, when you have impacts compacting the material within the crater, that's also decreasing your volume ratio. So by running the model with different volume ratios, that can provide us diagnostics of the degree to which our ejecta is escaping on Phobos. So here's an example of the evolution of topography over time, every 200 million years, of an average for when the volume ratio is 1. You can see that the average altitude of the surface for these 20 meter by 20 meter squares is slowly decreasing over time. But I'm also showing up here the altitude of the highest point within that grid and the altitude of the lowest point on average within the grid. So this is of the 100 runs, the average altitude of the lowest point. So you can see that the difference between the highest point and the lowest point is increasing with time. But here's another run where I did a volume ratio that was greater than 1. So basically, Phobos is getting fatter with time. And then here's back to the original run compared to 1 where the volume ratio is less than 1. And you can see that Phobos is getting thinner in time in this simulation. And you have less of a difference between the highest point and the lowest point. Now what really would happen is this material that's escaping is going to reaccrete on Phobos, but it's going to be more evenly distributed around. So what you can do to account for that is just displace all of these lines up with time, and the amount that you move them is the amount that you need to account for the fraction that actually does re-encounter Phobos. But that's not going to affect your difference between the highest point and the lowest point. That's still going to stay about the same because the redistribution would be pretty much even within a square this size. So here is the thickness of the regolith, how it evolves over time with the different models. And you can see with the volume ratio of 1, you are accumulating a thick regolith. But with the volume ratio less than 1, it is not changing that much with time. And so if you can measure the thickness of the regolith, it can give you some diagnostics for what gardening scenario is going on at Phobos. Okay, thanks. And then I also use the model to calculate the RMS roughness of the surface. So if you have a laser altimeter in orbit that can give you the roughness, this is something that you can compare. But for those two scenarios, you can see that the roughness is not that different between the two scenarios. So impacts are, especially in the beginning, are converting bedrock into regolith. And we're seeing saturation occurring for our small impact craters with this gardening run. But the thickness of the regolith is related to the ejecta dynamics. And we can use that once we measure it at Phobos to help constrain those dynamics. So thank you.
I got a couple questions. One, how much of the regolith material is composed of the impactor volume? And the other question, how did you account for changes in porosity or density of the material?
That's a good question. Let me answer the second one first. I have not done any differences for porosity and regolith, and that's why I've only run it out to 1 billion years at this point, because as time goes on and you're breaking up and you're hitting into regolith, you're going to change the fraction of material that's escaping. And I have not accounted for that yet. So yeah, that's on my to-do list. And what was the first question?
Well, how much of the regolith is composed of the impactor volume?
Yeah, actually, my model does not specifically account for what material is coming from where. And yeah, I could include a parameter that that tries to determine like how much of the exogenous material you would expect to have in that layer, and as time goes on, see how that changes, because that would be, yeah, really interesting. Yeah.
Really nice talk, Dana. I'm interested in the really fine stuff. And as I understand from the work you've done, you're really looking at some of the larger particles. So I'd like to pose a question that either you can address or Dan can address, or we should address in the discussion session of what about this gravitational regime, and what happens to the really fine particles? Do they accumulate? Do they redistribute? Because ultimately that's what we're seeing on the surface, and I really don't get a good sense of what some of the models predict.
Right, yeah, I mean, what I've done in the past with my gardening model more for the moon than this is not treat the fine stuff specifically, treat it all on average. And, you know, for the moon, we have all of the great data from Apollo that has helped us be able to account for that. And for Phobos, I don't know the constraints to put on that. So it's a hard question.
There's been some work that suggests that things smaller than 40 microns might get swept away, but pretty small before you lose that from the Mars system.
Thanks. Bill? Or, I don't know. Yeah, I'm sorry.
The question I had was about Jim Richardson's work. So Jim has some recipes for how seismic shaking should affect small bodies. And I would think that would be something you could implement in your model. Have you thought about doing that?
Yeah, I have thought about doing that. And also, I mean, there are a lot of things that I have not included in the model just to make it so that I can get answers in a reasonable time. And I have not accounted for any sort of redistribution of material from shaking or slumping or anything like that. And yeah, it's something that is really important and is going to affect the final, you know, roughness and the thickness and everything like that. And it does need to be accounted for somehow.
All right. We're going to have to cut it there. The bad news is that's the end of the questions. The good news is that we have our discussion section starting in 5 minutes. So I am here to announce to you that you have 5 minutes to have a break.